So we know that the determinant sort of can tell you the volume of the parallelepiped, or the tipped box, determined by some vectors. But what if, rather than just having a collection of vectors, you start with one collection of vectors, and you have a matrix, and you multiply by that matrix A to turn all of your vectors, the V's, into these other vectors, W. So now we have two parallelepipeds. We have one parallelepiped determined by the V's, right, like this. Maybe I shouldn't have tried to draw this picture. That's supposed to be a parallelepiped. Okay. The matrix A, multiplying by the matrix A, gives us another parallelepiped like this. And you can see in general the volumes of the parallelepiped that we started with and the parallelepiped that we ended with, in general, they're going to be different. And somehow it's A that determines how these volumes are related. Maybe what we could do is find the ratio of the volumes. So maybe let's find the volume of the parallelepiped determined by the W's divided by the volume of the parallelepiped determined by the V's. Okay, but the volume of the parallelepiped determined by the W's, so I guess I should have absolute values around these, because these might be positive or negative depending on the orientation of the V's or the W's, but anyway. So we know to find the volume of the parallelepiped determined by the W's, we can just take the determinant of a matrix whose columns are the W's, like this. And to find the volume of the parallelepiped determined by the V's, we can take the determinant of a matrix whose columns are the V's. But the W's, how did we find the W's? The W's are just A times V1. So this determinant upstairs, we have A times V1 for the first column down to A times Vn for the last column. And then in the denominator, it's just the determinant of this matrix made out of the V's, like this. But if you look at this numerator, this is actually just the matrix A times the matrix built out of the V's, like this. And in the denominator, of course, we still have the determinant of the matrix built up out of the V's. But now in the numerator, we have the determinant of, we have the determinant of a product, a matrix product right here, and we know that the determinant of a product is the product of the determinants. So this is the determinant of A times the determinant of the matrix built up out of the V's. And the denominator is the determinant of the matrix built up out of the V's. But look, now this one cancels. And we're just left with the determinant of A. Right? So what we found is the ratio of these two volumes is just the determinant of A. In other words, the determinant of A, or really the absolute value of the determinant of A, is the factor by which multiplication by A expands volumes. Right? So that's even nicer than our last interpretation of the determinant, which was it tells you the volume of all of these vectors, because this treats A, rather than describing the determinant in terms of the columns of A, it actually describes the determinant in terms of A itself, right? It's treating A like a linear transformation, and it's describing the determinant in terms of that linear transformation, right? So the determinant of A is just an expansion factor that tells you how much bigger volumes get when you map things using the linear transformation corresponding to A. There are a couple nice ways to use this. One is directly. So suppose we have 4 vectors that determine a parallel pipette whose volume is 5. So these vectors, maybe these are the v's. If we multiply these vectors by this matrix, what is the volume of the result? So we could take all our v's, name a times all the v's, name those w's. So here we're asking for the volume of the w, of the parallel pipette resulting from the w's. But that, right, we know that, so the volume of the w's, we know it's the volume that we started with, which is the volume of the parallel pipette determined by the v's, times the determinant of a. Maybe with an absolute value, right? Because for volumes we don't care about orientation, so maybe we should put absolute values there. All right. Well, even though we don't know what these vectors are that we started with, we know that the volume we started with was 5. So, right, there's a 5 there. So all we really need to calculate is the determinant of A. Now A is 4 by 4, so calculating its determinant should be messy, but there's a column here, or actually a row, either one, that has a couple zeros in it, so that'll be nice. Let's expand across the second row. So determinant of A is, so across this first row the signs are going to be minus, plus, minus, plus. So first two entries give us zeros, and then minus 3 times the determinant of, it's a 3 by 3 determinant, so 2, 0, 2, 3, minus 2, 2, and then minus 1, 2, 1. Okay, plus negative 1 times the determinant of 2, 0, minus 1, 3, minus 2, 1, minus 1, 2, 3. Okay, so minus 3 times. Now for this determinant going across the first row is going to be nicest, because then we get to pick up that 0 there. So let's see, 2 times this 2 by 2 determinant in the bottom right, so that's minus 2, minus 4, so minus 6, and then plus 2 times, and then the determinant in the bottom left, so that's 6, plus 2, 6 minus 2, so 4. Okay, plus negative 1 times, and now this determinant, so again let's go across the first row, so we pick up that 0 there, so 2 times negative 6 plus 2, so negative 4, it's this one, so then a 0, and then plus negative 1, sorry, I lost track of what I was doing. I'm going across this first row, so there's that 2, and then the next has a 0, and now I need negative 1 times this 2 by 2 determinant in the bottom left, so 6 minus 2, that's 4. Okay, almost lost it there. So minus 3, so here's negative 12 plus 8, so that's minus 4, minus, minus 8, minus 4, so minus 12. Okay, so it looks like 24. So this is 24 times 5, so 121. Right, there's 100 and another 20, 120. Okay. All right, so we started with a volume of 5. This multiplying by this matrix multiplies our volume by 24, and so our resulting volume is 120. I've been saying volume, but you know, this is all happening in R4, so really I guess I should be saying hypervolume. This is sort of a 4-dimensional volume, not a 3-dimensional volume. One other nice application of this fact about determinants, that it tells you how much a matrix expands volumes, is it can give you a shortcut for calculating determinants. So suppose we have a matrix that represents rotation in some Rn. Right? Now this could be any rotation at all. It doesn't have to be one of the simple rotations about a coordinate axis. It could spin, I don't know, in any old way. Right? That is a linear transformation. And what is its determinant? Well, rotation, on the one hand, doesn't change volumes. Right? Whatever, if you start with a shape of any volume and you rotate it in any way, it has the same volume. And also, it doesn't change orientation. Or, I guess, handedness. Right? Whatever handedness your vectors started out with, if you do a rotation, you still can use the same hand to describe those vectors. So, well, this first fact tells us that the absolute value of this rotation matrix is 1, and the second fact tells us that the sign of the determinant has to be plus, and together these mean that the determinant for this rotation matrix has to be 1. So every rotation matrix has a determinant of plus 1. And we were able to calculate that without actually calculating any determinants of rotation matrices, which is good because, right, this is true for any rotation in Rn. And this would be impossible to prove by actually calculating determinants because there would just be too much work to do. But right, instead we get to skip all that work and just know the value of the determinant for any rotation matrix in any dimension.